All right, hello everybody, welcome back. We're going to be working on section 6.2, and section 6.2 is known as the real applications of normal distributions. And again, this is just a continuation of the continuous data that was displayed with a standard normal distribution. All right, now we have experienced z-scores before, and we're going to keep working with them today. All right, remember, z-score is just a standard deviation that has been standardized. All right, and standardized means that we've applied the standard normal distribution, where we start looking at the mean being 0 and the standard deviation being 1. So anytime that we want to get a z-score, the z-scores are always going to be relatively small, meaning they're going to be between 0, -1 or 1, -2 or 2, or -3 and 3. All right. Typically, they don't go beyond -3 or 3. So, let's start looking at this. On screen here, you have some formulas that we're going to be using. These formulas that we're going to be using are going to allow us to standardize any given score. All right. So, the two formulas given here are the exact same formula. The first one here is just used for a sample, and the second one is used for population. Now, again, the only difference is the notation that we use, but essentially it's the same thing. One bigger aspect, this round-off rule. The round-off rule, we're always going to consider that every z-score that we use must be rounded to 2 decimal places. All right, so that's awesome. Now, let's start looking at this example that says, consider your height in inches. Calculate the standardized value, in other words, the z-score, for your height, given that in the United States, the average height for women is 63.7 inches, with a standard deviation of 2.7 inches, and for men is 69.1 inches, with a standard deviation of 2.9 inches. So the big question is, would you be tall for your gender? All right, so I'm going to give you all my height. So my height, I am 5 feet and 11 inches. On a good day, 5 feet 11 inches. This will automatically translate into about 71 inches. All right, 5 times 12 should get us, 5 times 12 should get us about 60, and then 60 plus 11 should get us at 71. Awesome. So what I'm going to do is I'm going to convert my inches, my height in inches, into a standardized score. All right, so I'm going to go with that 71 here minus the mean for all men's heights in the United States. So the average of those men's heights was 69.1 divided by the standard deviation for all of men's heights, which is 2.9. So all I do from here is just put this into the calculator. 71 minus 69.1, and then you're going to divide by 2.9. So here I get, and again, z-scores, 2 decimal places, I get 0.66. So as we start looking at this, I'm going to start answering the question. And again, the question here is, would you be considered tall for your gender? Now, this question, a lot of people might say, well, yeah, I'm tall, right? But again, what I wanted you to do is use the numbers and use the theory that we've been crafting in this class. In order for somebody to be considered tall within this particular aspect, we want to make sure that tallness is measured by somebody who is unusually tall or unusually small, meaning we need to pass those 2 standard deviations. Look at my score here, 0.66. That's within the 2 standard deviation rule, which means I am not tall. I am not considered tall. So this is within 2 standard deviations, which means I am not tall. Sad face, not tall. All right. So now the question then becomes, what is the probability that someone of my gender is taller than you? All right. Well, that kind of seems like a question from last time, so let's see if we can go through it. All right. Again, what I'm doing here is I'm using the standard normal distribution, and I'm using my z-score. So my z-score, the one that I am looking at, is 0.66. That's about here. All right, that was 0.66. And what I'm trying to find is a probability that someone is taller than me. All right. So in other words, I need to find this area. That's what this question is really saying. Find that area. So if you remember from last time we were in the process of finding a probability or finding a z-score. I want to find a probability, which means what I'm looking for the probability that somebody's z-score is taller or is larger than my z-score. Now, what does that mean for us? Well, that just means we're going to do normal CDF. I need to input the interval. The interval for the blue area, well, the interval for the blue area starts at 0.66, and then it heads to the right because it's a right tail. Now remember, anytime that it heads to the right, we do that 1E99 in order to suggest that this tail goes on for a really long time. All right, that way we can find that probability. We do a mean and a standard deviation. So let's go over to the calculator and see if we can get that going. Here we are. We're going to go to distribution, and again, that distribution is right here as I'm highlighting it with my mouse. So second distribution, there we go. We're going to go to normal CDF, press enter. Lower bound, that was at 0.66. Go lower a little bit. That upper was 1. And then that double E. Remember, we don't do capital E. We do this blue. We do this blue double E. That's going to get us at E99. We go down, down, down. Awesome. Everything looks good. Paste that. Looks like I had it on my screen. There we go. There's my probability. So what I'm going to do is I'm going to take about 3 digits here. So that's going to be 0.255. So let's go back. 0.255. Here we are. 0.255. So the probability that somebody in the United States is taller than me is about 25.5%. Wow, that's interesting. All right, that's not bad. Not bad. All right. So now that we have this, now that we've built all this, let's go ahead and see if we can answer some of these questions. All right, so here's this example that says the average for the statistics exam was 75, and the standard deviation was 8. Andre was told by the instructor that he scored 1.5 standard deviations below the mean, and the scores were normally distributed. What was Andre's exam score? All right, so we have a few things to do here. All right, so let's go ahead and see if we could try to highlight what we need, what is given, and what's going to be pertinent to us. All right, so I see here that the average, all right, so they're giving me an average here. They're giving me a standard deviation. So I see average, I see standard deviation, and he was told by the instructor that he scored 1.5 standard deviations below. I'm going to highlight that in red here. 1.5 standard deviations below the mean. And then the super important part is that the scores are normally distributed. All right, so we got some work to do here, and let's see if we can try to extract what we need. All right, so again, what I'm going to do here is I'm going to do z-scores. So as I'm working with these z-scores, they're going to be 0, 1, 2, 3. Whoa, that's a bad 0, 1, 2, and 3. Let's go ahead and let's, come on, work with me here, technology. 0, 1, 2, 3, and these are z-scores. Wow, this technology does not want to work with me today. I had some issues with it earlier today, and there we go. It's been quite a learning experience for everybody, so hang in there, hang in there. All right, so here we go. Let's start extracting everything that we need. All right, so I'm going to look at my average. That average was 75, so I'm going to extract that, and I'm going to write this in green. That way I can start looking at this. All right, so the average was 75. The mean, standard deviation was 8. All right, good. Now, Andre was told that he was scored 1.5 standard deviations below the mean. So if we standardize the mean here, he's actually saying 1.5 standard deviations. So that means Andre's score is here. So when we're looking at Andre's score, we're assuming that his score is negative 1.5 in the standard deviation notation. All right, so this is what we're trying to find, is what was his score there. All right, so what I'm going to do is I'm going to use that formula for z-scores. The formula for z-scores is this x minus mu divided by standard deviation. And so as you can see, I can start subbing in these values. All right, this is going to be negative 1.5 is equal to x. I don't know what x is because that's Andre's score. But I do know the mean, which is 75, and I do know the standard deviation, which was 8. So all I have to do here is, ooh, here goes a tough word. I have to perform some algebra. There, I said it. I have to perform some algebra in order to solve this. So what I'm going to do is I'm going to multiply by 8 on both sides. So in other words, you can think of this as cross multiplication. So I have negative 1.5 and I'm going to multiply by 8. That should get me 12. So this is 12 is equal to x minus 75. There we go. Oh, sorry, negative. My apologies. It's negative because negative 1.5 times 8. There we are. So what I need to do next is add the 75. So we're going to add the 75 to the other side. And when we add the 75 to the other side, we get 63. Now, I want you to stop and ask yourself, does this make sense? Right? Because if his score was 1.5 standard deviations below the mean, that means it was below the average. So this number, this 63, should be below this average, and it is. All right? Which means Andre's score is 63. And there we are. Now, one of the things that I like to do is I like to do this here. I like to get another axis here. And this other axis, the one that will sit right below the original z-axis, I typically want to call this the x-axis. Because whether you have x or whether you have z, you're still going to have the exact same answers. Now here, if I use the x values, then I'm only using the x values that I was given. The mean is 75. The standard deviation was 8. So if I move backwards, meaning 75 minus 8, then I get 67. Move backwards one more time, so 67 minus 8 again, and that's going to be 59. Which means Andre's score should be in here. And it is, because it's 63. Alright, so there are different ways to do this, and typically we like to use these different representations. And occasionally you'll see me using both of these representations, because whether I use z-scores or whether I use x values, both are always going to give me the exact same answer. Nice. So let's see if we can work with the next problem then. Let me erase this just a little bit. There we go. So the next example says that the lifespans of a brand of automobile tires are normally distributed with a mean lifespan of 35,000 miles and a standard deviation of 2,250 miles. The lifespan of a randomly selected tire is 34,000 miles. So we now want to find the z-score of the tire. All right, so there's the big question. There's the big question. Find the z-score of this tire. And then after that, it's going to say, can you find the probability that a randomly selected automobile tire has a lifespan less than or equal to 34,000 miles? All right, so there is what I have. Now I'm going to extract what I'm given. Now that I've identified what I have. So what is given to me, it says that you have a mean lifespan, so in other words an average, and a standard deviation of 2250. Nice. So then the lifespan of a randomly selected tire is 34,000. Okay, I have everything I need to know now. All right, so I have the mean, which was, let's go with the mean, so X bar was 35,000. There we are. I have a standard deviation, so standard deviation of 2250. A randomly selected tire, that's my specific X value, which is 34,000. All right, and I want to find the z-score. So all I'm going to do is I'm going to make my substitutions. So finding the z-score, I'm going to have 34,000 minus the 35,000, all divided by the standard deviation. All right, so here we go. So 34,000 minus 35,000, that should be a nice 1,000 divided by 2250. So 1,000 divided by 2,250, that should get us 4/9, in other words, 0.44. 0.44. There we have it. All right, not too bad. Any questions so far? That's what I would typically ask. And yes, you'd absolutely be correct. Person in the back. This is a negative. All right, why is it a negative? Because it's 34,000 minus 35,000, which means we're naturally going to get a negative value. Perfect. Okay, so find the z-score of the tire. All right, so that first one is now done. So we got the first part done. The second part says, can you find the probability that a randomly selected automobile tire has a lifespan less than or equal to 34,000 miles? All right, so what I'm going to do here is I'm going to use my z-scores. 0, 1, 2, 3, -1, -2, -3. I'm looking at this z-score. It's negative 0.44. Okay, so negative 0.44, that's close to a half here. All right, that value is negative 0.44. There we are. And the probability that I'm looking for, it says, can you find the probability that a randomly selected automobile tire has a lifespan that's less than or equal to this? Now, remember, as you're doing this, we came up with a process last time that said if I'm looking for a probability that some z-score is less than or equal to negative 0.44, remember, it doesn't matter if this has an equal or not, because at the end of the day, this is a continuous probability, and continuous probabilities don't matter whether we have an equal or a strict inequality. So in here, I need my normal CDF. I'm going to insert my values. Let's see, my shaded area goes to the tail. That's the left tail. Because it's a left tail, I need one E99. It stops at negative 0.44, mean, and standard deviation. Let's go to the TI and put this in. Here we are. So let's go to NormalCDF. There we are. Lower was at -1 E99. Upper was 0.44, excuse me, -0.44. There we are. Mean and standard deviation were the same. Paste that. There we go. There's our probability. Take 3 decimal places, so it's going to be 0.329, or we can call this 0.330. So here we go. So there's our probability. Now, if we wanted to, we could express this as a percentage, and that percentage would just be 33%. So the probability that a randomly selected automobile tire has a lifespan less than or equal to 34,000 miles is roughly 33%. Interesting. Now, the big question then becomes, do we actually need to convert into z-scores, or, like in the previous example, can I do this just using x values? The answer to that is yes. We can do this without converting into z-scores. But there's a small issue with that, and I'll tell you what that small issue is as we're illustrating this using z-scores. Or sorry, using x values. All right, so here's the issue with this. If I want to find the probability that some random selected tire has a lifespan that's less than or equal to 34,000 miles, what I can do is I can still do my NormalCDF. I need a really small value for my x values. Or let's think about this. I need a really large negative value, which means -1 e to the 99 still suffices here. The stopping point for this shaded region was this z-score, but this z-score corresponds to this x value, which is a 34,000. And we have to be careful here because the mean and the standard deviation are not 0 and 1, respectively. The mean is actually what we were given, which is 35,000. And the standard deviation is actually 2,250. So what we want to do at this point in time is we want to input this into the calculator to see what we actually get and see if it's going to be the same answer. So let's go back to the TI. All right, here we are back at the TI. I want to access that NormalCDF again, so let's go to NormalCDF. There we are. -1 E99. My upper bound was at 34,000. There we are. My mean was at 35,000. Standard deviation was 2,250. There we are. So that looks exactly like I wrote it down on my whiteboard. And I'm going to hit enter. There we are. So look at this answer. Again, take about 3 decimal points. 0.328. Now, I want you to compare your 2 answers, right? Your 2 answers almost identical. There's only an issue, is that this answer isn't quite as good as this answer here. All right, and the reason why that is because this -1 E99, it's actually not that large compared to all of these values, right? Because these values are already, in our sense, large. But when we use it in comparison to the z values, where the largest we can get is -3 or 3, then this value, -1 E99, becomes extremely large, which means it goes out far enough for what we need. So, can we do this without using z-scores? Yeah, we definitely can, and that's using this process. All right, so at the end of the day, you're more than welcome to pick whichever method you'd like. All right, so now, when to use NormalCDF and when to use inverse norm. So, to find a when we want to use NormalCDF, we want to find a probability when the blank is given. All right, so what needs to be given in order for us to use normal CDF? All right, so when normal CDF is given, typically we have a z-score given to us. If the z-score is given to us, that means that we must have the mean, standard deviation, and the x value. Nice. When to use inverse norm. When we use inverse norm on our calculator is when the percent or the area of the probability is given and we are trying to find the z-score. So when we're trying to find the z-score, we use inverse norm. When we're given a z-score, or when we're given a mean, standard deviation, and an x value, then we use normal CDF. So what we want to do now is we want to keep going with this process, and let's see if we can finish off some of these examples. So the completion times to run a road race are normally distributed with a mean of 190 minutes and a standard deviation of 21 minutes. All right, so there's a few things to highlight here, a few things that are given to us. So they're giving us that we have a mean of 190 minutes and a standard deviation of 21 minutes. All right, so I'm going to extract that really quick. So I have a mean of 190 minutes and a standard deviation of 21 minutes. There we are. So the question here is, what is the probability? All right, so keyword here, what is the probability that a randomly selected runner will finish the race in less than 150 minutes? So my process here is going to be to standardize this. As soon as I can standardize it, then I'm going to find that probability. All right, so let's go ahead and let's try to standardize this first, which means we got to find a z-score. So see, z-score, I need 150. I'm trying to standardize that 150. So 150 minus the mean, which was 190, divided by 21. All right, go to your calculator and do 150 minus 190. That's negative 40. So negative 40 divided by 21 should get us a z-score of negative 1.90. Nice. So now that we got the z-score, we have enough, or we've done enough to standardize it. All we got to do is put it into a probability now. So this is the probability that the z-score will be less than 150. Oops, excuse me. And 150 has a z-score of negative 1.90. Alright, so that was 0, this was negative 1, negative 2, negative 3, 1, 2, and 3. So that means for us, that z-score, negative 1.9, somewhere here. And I want everything to the left. Which means I'm going to need a normal CDF. Left tail, that means negative 1E99. Stopping point is at negative 1.9. Mean and standard deviation, I standardize this, so I'm using 0 and 1. Nice. All we have to do is now go to the calculator. So let's go to the TI, let's put this in and see what we get. All right, here we are. There we go, and that was negative 1.9. There we are. Mean was 0, standard deviation was 1, and I'm going to hit enter. There we are. So there's my probability. 0.0287. So 0.0287. Here we go. There we are. So there's a probability that we're looking at. Now the question some of you all may be asking is, could I do this question? Could I do part A without standardizing? Yes, you can. You can do it without standardizing because you're given a x value, you're given a mean, a standard deviation, and the x value, which means going through the process that we did before, and that was the one here on the margin, going through this process is still going to give you the exact same answer. So if you want to give that a shot, go ahead and do so. All right, see if you get the same answer now that you know what the answer needs to be. All right, so part B, what percentage of runners will finish the race between 205 and 245 minutes? So again, what I want to do is I want to standardize this. So let's make sure we work with the standard normal distribution here. That's 2, that's 3, -1, -2, -3. And let's standardize these values. So the first z-score that I want to find out is, what is 205 going to be as a z-score if the mean is still 190 and the standard deviation is still 21? And what is the other z-score going to be? And I'll figure that out in a bit. So 205 minus 190, there we are. That's going to be 15 divided by 21. That's 0.71. The next z-score that I want is the one that's going to produce 245 minutes. 245 minus 190 divided by 21. So you go to your calculator, you do 245 minus 190, and then you divide by 21 to get you 2.62. So these z-scores, 0.71, 0.75, or sorry, 0.71, somewhere here, and then we have 2.62. 2.62 is going to be somewhere here, 2.62, there we are. Which means we're looking at the area here between those two values. So we want to find the probability that the z-scores are between 0.71 and 2.62. Just like that. All right. This looks kind of ugly, so that's going to be 0.71 less than, there we are. So we need a normal CDF. Normal CDF. Left endpoint, that was 0.71. Right endpoint, that was 2.62. Mean and standard deviation was 1. Nice. So let's go through and let's input this on the TI-84 and see what we get. Here we are. I need to go to normal CDF, so I'm going to go second distribution, go down to normal CDF. My leftmost endpoint for the shaded area was 0.71. My rightmost endpoint for that shaded area was 2.62. Mean and standard deviation were standardized. So all I need to do is hit enter, and there we have it. We get this answer of 0.234. Awesome. Here we are. So the probability, or the percentage, excuse me here. So the percentage that we were looking for, again, I'm not completely done because the percentage here is then going to be 23.4%. This is the answer that I want. Because it's asking me for percentage, I need to give the answer as a percent. Whereas in the previous question, part A, it said probability. So in this particular case, the percentage of runners that will finish between this interval given, 205 minutes and 245 minutes, is roughly 23.4% of the runners. Awesome. Awesome, awesome. Now, I want you to try to extract all the information that is given for this example and try to identify what is the question that's being asked and see if you can solve it. In a little bit, I'll walk you through it to make sure that we're all on the same page. But again, I want you to attempt it by yourself, because at this point in time, we have everything at our disposal to answer part A and part B. All right, so take some time, get that done, and I'm going to take a little break, and I'll come back and check on you all in just a bit. All right, so I hope you all tried it on your own. Here is what I extracted from it. that a construction zone on a highway has a posted speed limit of 40 miles per hour. The speeds of the vehicles passing through the construction zone are normally distributed. So that's a key phrase. All right, normally distributed. If it's not normally distributed, we have an issue and we can't go further. So it's normally distributed, and it's telling us that the observations provided a mean of 46 miles per hour and a standard deviation of 4 miles per hour. So that extraction happened here. Now, the reason I extracted 40 is because the question for part A says what percentage of vehicles exceeds the speed limit. Well, what was this posted speed limit? That was 40 miles per hour right here in the given. So I extracted all of this. I standardized that 40 miles per hour to give us a z-score of negative 1.5. And then since we're interested in finding a probability for what values exceed that amount, we have to shade everything to the right. Shading everything to the right using our normal CDF gets us negative 1.5 all the way to the right, mean and standard deviation, 0.933. But the question wants a percentage, which means 93.3% of the cars will exceed that speed limit. Wow, that's interesting. So I guess if you want to say, can somebody change that speed limit? Well, we can go ahead and we can run some statistics in order to see will it then benefit that street, right? Or that flow of the traffic. And this is one of those considerations that cities look at when they're talking about increasing a certain speed limit. All right, so next question, part B. It says, if the police wish to ticket only those drivers whose speed falls in the upper 20th percentile, all right, upper 20th percentile here, what is the speed limit? So what is then the speed limit, or what is the minimum speed limit of a driver that will be ticketed? All right, so, whoa, let's go back on that. There we go, perfect. So let's extract what we have here. They're giving us this percentile. So they're saying the percentile of the 20th percentile is what we're looking for. Now they're saying upper 20th percentile. So I'm going to focus on that as well, that it's an upper 20th percentile. Now remember how we were looking at probabilities and how we were looking at percentages. If this is a 20th percentile, then this implies that it's just 20%. In other words, it's 0.2. This is the probability. In other words, this is that shaded area to the right. Upper means it must be to the top, meaning to the right. All we need to do is find out what are those values. -3. There we go. So in here, what we want to do is we want to find a z-score. Once we find the z-score, then we're going to be able to extract what is that x value. All right, awesome. So I want you to find me that z-score. You're going to have to use inverse norm. So go ahead, see if you can try to do that. Put pause on the video and see if you can do it. I'll come back in a little bit and I'll write the answer down. All right, so here's what I get. I get 0.84. So that's the z-score that I get, 0.84. Now, how is this going to help me? Well, I need to go through the process of getting the x value. In other words, that speed that I'm looking at. Because everybody up here is going to get ticketed, and I need this exact value. Now that I know the z-score, I can go through and I can find that x value. So the z-score was at 0.84. The x value minus the mean. Well, what was the mean that we're using here? Well, we're going to have to go through and extract it. The mean was 46. Standard deviation, 4. All right, so let's go through. We're going to take 4 and we're going to multiply it by 0.84. There we are. So this is going to get me 3.36 is equal to x minus 46. Finally, I need to add that to both sides, which means I need to just add 46 to it, which means my speed is going to be 49.36. So, what is the minimum speed that a driver will be ticketed if a police officer wants to only target the 20th percentile, the upper 20th percentile? Well, the minimum speed will be 49 miles per hour. Interesting, because again, this posted speed limit is 40. Everybody's on average going 46, which means if you go 49 and the officer's only looking for the top 20th percentile, then hey, you're going to be good. All right, so there it is. And that's actually going to wrap up section 6.2. And shortly we'll start on 6.3, and I'll see you all then.